good morning students. In the today's video we will discuss about the digital frequency meter. It is mainly used for measuring the frequency of the input signal. Okay, so whatever the signal you are having, if you would like to calculate the frequency of the particular signal, then we are using the digital frequency meter. So the principle which is followed by this particular frequency meter is, that is a digital frequency meter, is first of all it will take the unknown signal. It will take the unknown signal. Forget about these blocks, we will come to that one. This signal is converted into equivalent pulse format now. Okay, now so these signals are converted into the square pulses. Okay, so these pulses are fed as an input to the counters, by using one switch. Okay, now so how many number of pulses this particular switch, whatever the switch we are having over here now, this particular switch is open for open and close, means it is controlled by a control signal. Okay, now it is controlled by a control signal, and this control signal takes the responsibility to close the switch as well as open the switch. Whenever the switch is closed, whatever the square pulses we have, those square pulses are fed as an input to the counters. So we know that the counters are the good to count the number of pulses which are applied as an input to this particular device. Okay, so counters are the pulse counters, but how it is going to be counts, that purely depends on the when the switch is closed. At that time only these counters are able to count the number of pulses which are given as an input to this particular device. Okay, now which are given as an input to this particular device. Now the thing is, here this particular switch is open and closed. Now it is controlled by one thing called as a control signal. I'll come to this particular control signal. We have the elaborated explanation for this one, but this control signal is closes this particular switch for some period of time. Means this control signal is a time measurement element. It is a time measurement element. Okay, now so it is a time measurement element. So this particular time measurement element will close this particular switch for some period of time. So within that period of time, how many number of pulses are counted by the counters? How many number of pulses which are counted by the counters? So I'm assuming that count as a what is it? I'm assuming that count as a capital N. I'm assuming that counter as a capital N, means n number of pulses are, I'm assuming that the counter is counted the n number of pulses during the time period. I'm assuming that the switch is closed for the time period of small t. Okay, now so the switch is closed for the time period of the small t, and within this particular time period the number of pulses which are counted by the counter are n. The number of pulses which are counted by the counter are n. Okay, now so I know the time period, I know the number of pulses counted by the counter, then I can easily show that, means this frequency meter can easily calculate the frequency of the unknown frequency of a input signal. So means in order to show the frequency of the input signal, we are taking the formula F equals to the N by T. Okay, now so using this particular formula, the digital frequency meter is able to show the frequency of the unknown signal. The digital frequency meter is able to show the frequency of the unknown signal. So I'll come to the rest of the blocks. Just remember that whatever the unknown signal is there, that unknown signal is converted into the, means I'm assuming that the unknown signal is a what is that sinusoidal wave. This particular sinusoidal wave is converted into the pulse format. This particular sinusoidal wave is converted into the pulse format, and these pulses are given as an input to the counters via the switch, and this switch is open and closed, that is decided by the control signal. And I'm assuming that this switch is closed for time period of t, and within this time period how many number of pulses are counted by the counter is, I'm assuming it as a n. Okay, now so after time period t, I'm opening the switch. So when I'm opening the switch, obviously the pulses won't be fed as an input to the counters. So the counter is unable to count the number of pulses. Now, so the n is nothing but the number of pulses which are counted by the counter within the time period t. Then the frequency of the unknown signal, that is the frequency of the input signal, can be easily calculated by using the formula n by t. Can be easily calculated using the formula n by t. So this is the principle. Principle of the digital frequency meter is nothing but whatever the frequency, whatever the input signal frequency you would like to calculate, that input signal is in the form of the sinusoidal wave, and that sinusoidal wave is converted into the square pulses, and those square pulses are counted by the counters, and the pulses are fed as those the number of pulses which are counted by the counter should within the given time period, within that given time period. So if you take the ratio between them, then it is a frequency of the input signal. It is a frequency of the input signal. Okay. So the principle is the number of pulses which are counted by the counter during the time period t, that is nothing but the digital frequency. That is a frequency of the your input signal. That is the frequency of the your input signal. Okay. So now let us come to this one. Okay. So the block diagram. First of all, here I am assuming that I am having the unknown signal. Okay. So this unknown signal is in the form of the sinusoidal wave. But as we know that whenever you would like to measure the unknown signal, whether you would like to feed the input signal, which is the unknown signal, as an input to the device, obviously you are supposed to perform the amplification process, because the intensity which is for intensity of the signal which is there in the input source may not be sufficient to drive to the end device, to drive to the end block of your device. So because of that, we are simply performing the amplification. We are simply performing the amplification. At the output of this particular amplifier, we are having the what is that high intensity input signal, means the same unknown signal is there, which is the amplified signal. At the output of this one, we have the amplified signal, and these amplified signals are given as an input to the Smith trigger. We know that the Smith trigger is the one which will convert the sinusoidal wave into the square wave. Sinusoidal wave into the square wave. Remember, ma, for every cycle there is a equivalent pulse, ma. For every cycle there is a equivalent pulse. Remember that point. For every cycle of the input signal, the Smith trigger will show the equivalent pulse. The Smith trigger will show the equivalent pulse at the output. Okay. Now, so the Smith trigger is the one which will convert the sinusoidal wave into the square wave format, that is the pulse format, and these pulses are given as an input to the counters. These pulses are given as an input to the counters via the a switch. So here this I'm saying it as a switch, but here we are using the gates now. So we'll see the one more block diagram for you, our digital frequency meter. Don't worry about it. So here this we have the switch, and this switch is controlled by the timer now. So this switch is controlled by the timer, means I'm using the control signal, and that control signal decides the how long you would like to feed the pulses as an input to the counter. How long you would like to feed the pulses as an input to the counter, so that the counter counts the number of pulses. And after that period, let us suppose, as I told you, that if the time period t elapses, so after this time period the switch is automatically open. So during this time period the switch is closed, and after this time period the switch is automatically open. So after that, the inside the device we have the calculator, which will calculate the ratio between the number of pulses counted by the counter by the time period, and finally it will show the frequency of the unknown signal. Finally it will show the frequency of the unknown signal. Okay, now so here whatever the controls, I'm saying that this is a control signal which is the what is it, controlling the switch, which is controlling this switch na. So this control signal generator is called as a time based generator. Okay na. So which is called as a time based generator, so which looks like this. So I'm just taking the this particular part now. Okay, so this part is okay. So we took the input signal, and as it is having the low intensity, I'm just fed it as an input to the amplifier. So at the output of the amplifier, I'm having the high intensity signal, which is given as an input to the Smith trigger. Smith trigger is the one which will convert the sinusoidal wave into the square wave format, and these pulses, these square wave signals are given as an input to the counters, and through the control signal through the switch, and this switch is controlled by the controller. Okay, now so that is a so this switch is open and closed based on the time period. So that controlling block is called as a time based selector, which will show like this. Okay now, so which is like this. So here the time based selector we have now. So the time based selector is the one which will decide how long you would like to close the switch, means how much time period you would like to close the switch. How much time period you would like to close the switch, that is decided by the time based selector, and this particular output signal, this is the output signal from coming from the time based selector. This particular output signal is given as an input to the what is that, start and stop gate, or I can say that it is a switch. It is giving the input to the switch as a control signal. Okay, so now, so this particular time based selector is implemented, means we are generating the different time periods now. We are generating the different time periods. How long you would like to measure the number of pulses and take the ratio between the number of pulses and the time period. It will show the frequency of the signal. So how long you would like to measure the signal, that is decided by the time period, and that time period is generated by the time based selector. So this particular time based selector generating the what is the time delays with the help of the clock's oscillator, with the help of the this particular oscillator, crystal oscillator. Okay, so we are taking the crystal oscillator for generating the required time period, the required time periods. Okay, so I'm assuming that this is a what is that, crystal oscillator, and whatever, in order to get the accurate time delay, in order to get the accurate time period, what we are supposed to do means, whatever the clock generator we have, the crystal oscillator clock generator we have, we should place this one in the temperature. We should place this one in the safe container, which will not affect the affected by the external parameters. Okay, so that's why we are placing this particular crystal oscillator in the safe case, and the output of that one is given as an input to the Smith trigger. Okay, so the crystal oscillator, as we know that it is generating the sinusoidal wave. I'm assuming that this particular crystal oscillator is generating the 1 megahertz 1 megahertz frequency sinusoidal wave, and this particular sinusoidal wave is converted again back into the what is that, a square wave with the help of the Smith trigger, and the frequency of the signal is not changing. We are simply converting the sinusoidal wave into the square wave format. We are simply converting the sinusoidal wave into the square wave format. And now, if you see this one, this is the square wave format now. So I'm taking the this is the frequency. If you are converting that one into the what is the time period format, the ratio, that is a reciprocal of this particular one, is nothing but the 1 microsecond. Okay, so I can say that the frequency time period t is nothing but, or I can say that the time t is equals to the time t equals to the how much ma? That is a 1 by frequency, 1 by f. So if you take the ratio of the frequency, then you can easily calculate the time, and vice versa. If you take the ratio of the time, you will get the frequency. So here we have the 1 megahertz signal na? So 1 megahertz signal, and it is given as an input to the divider. We have the 6 dividers over here, 6 dividers. So each divider is having the denominator as a 10. Okay, now I can say that there is a divider with decimal number. So first divider, second divider, third divider, fourth divider, fifth divider, sixth divider. So at the input of the first divider, we are taking the output signal. So this particular element is giving the 1 microseconds delay, and at the output of the divider 1, so it is dividing the 1 megahertz with the 10, 1 megahertz with the 10. Okay, so as it is dividing 1 megahertz with the 10, then it is called as a 10 microseconds. Okay, so it is called as a 10 microseconds, and another case is a 100 microseconds. So division is nothing but, it is a division means it is a 10 to the power of minus 1. So just remember that we have the 1 megahertz now. Simply I can calculate this one like this. Okay, wait a minute. So we have the 1 megahertz, 1 mega. So I'm just taking the, yeah, 1 megahertz. Let me go with the 1 megahertz itself. 1 megahertz. 1 megahertz is nothing but, I can write this one in terms of the what is that, 1 megahertz. If I'm dividing this 1 megahertz with 10, 1 megahertz with 10, then I can rewrite this one is equals to the 1 into uh, 1 into, sorry, 1 into 10 to the power of minus 1, 10 to the power of minus 1. Okay, it is a 10 to the power of minus 1. So if you are dividing that one with 10, it is a 10 to the power of minus 1. If you are dividing this, means this is a divided with a 10, this is divided with a 10 means 10 by 10 means it is 100. Okay, so 1000, and what is it, 10,000, and this number goes on increase, this number goes on increase. It is a 10, So again divided by 10 means we have the 1 by 10 over 10. So here again we are having the one more division 10. 10 means 1 by 10 whole by 10 is nothing but the 1 by 100. 1 by 100 means 10 to the power of minus 2. So it is a 1 by 10 means it is a 10 to the power of minus 1. 1 by 100 means it is a 10 to the power of minus 2. So if you see this one, we have the 1 microsecond, which is a multiplying with the 1, and it is a multiplying with the 10 to the power of minus 1, which is nothing but the 10 microseconds, and 100 microseconds, 1 millisecond, 10 milliseconds, 100 milliseconds, and 1 second. Okay, so like this we have the time based selector, means we are simply taking the crystal oscillator to generate the frequency signal, and that frequency signal is, that sinusoidal wave is converted into the square wave, and this square wave signal frequency is divided with the frequency divider circuit. Before this one we have the 1 megahertz, so it is multiplied with the 1, means 1 megahertz means reciprocal of the 1, the 1 by 1 megahertz is nothing but the 1 microsecond, and 1 by what is it 1 megahertz is a microsecond. So it is a 1 by 10. Frequency is a 1 by 10, means 1 by 10 means it is a 1 into 10 to the power of minus 1. 1 into 10 to the power of minus 1 megahertz. 1 into 10 to the power of minus 1 megahertz means if you take the reciprocal of this one, it will come the 10 microseconds. It will come the 10 microseconds. What I mean to say that, yeah, it is a 10 microseconds. If you go for the mathematical calculation, you will come to know that one. If you want to know that one, it is a 1 into 10 to the power of minus 1 megahertz, right? Megahertz. So megahertz. Okay. So if you take the reciprocal of this one, so reciprocal means the 1 by 1 by 1 into 10 to the power of 10 to the power of minus 1. 10 to the power of minus 1. 1 by 1 into 10 to the power of minus 1 means it becomes a 10. It is which is equals to the 10, but it is was there, this frequency was there in the denominator, no? So it is there in the denominator, so obviously it becomes a hertz is in the denominator, means obviously it becomes a seconds, but in the denominator we have the mega also. Mega means it is a micro, so means I can simply say that it is a micro seconds. It is a microseconds which we are having over here: 10 microseconds, 100 microseconds, 1 millisecond, 10 milliseconds, 100 milliseconds, and 1 second. Okay, so don't get confused with this one. You simply just realize that this is a time period time based selector to select the time period. So at the output of this one we have the 1 microsecond, 10 microseconds, 100 microseconds, and that period depends on the switch selector. Okay, so to which time period, means how long you would like to measure the number of pulses, that is decided by the by choosing uh, this particular switch. If I'm connecting to this particular switch, then the number of pulses which are fed as an input to the counter, it is accepted for 10 milliseconds, and the number of pulses counted within that time period is if I'm assuming it as a n, then the time period is a 10 milliseconds. Then obviously output becomes a it is a 10 milliseconds. Then obviously this is equals to the frequency of the what is that input signal. It is the frequency of the input signal. Okay, so the time based selector is nothing but which is used for selecting the time period. Simple cases which is used for selecting the time period. Okay, so once we done with the time period, we done with the what is that time based selector. Okay, let us go for the actual block diagram of our digital frequency meter. Okay, if you please take this one, from here, yeah, let us go for the blocks first. Here we are applying the signal, whose frequency we would like to calculate, means unknown frequency signal is given as an input to the Smith trigger. So this is a block which receives the input signal, whose frequency you would like to calculate, and this input signal is given as an input to the Smith trigger. Obviously this one is converting the Smith trigger, converting the sinusoidal wave into the square wave pulses. Okay, no, square wave pulses, and it is given as an input to the what is that, AND gate, one of the input of the AND gate, and this AND gate is acting as a switch. Okay, no? So this AND gate is acting as a switch. Okay, so these pulses are fed as an input to the counter, means here we are having the counter, block. These pulses are given as an input to the counter block. Okay, now. So the pulses are counted by the counter. The pulses are counted by the counter. This is a counter block. Okay. But these pulses are given as an input to the counter, and whether these pulses are forwarded as an input to the counter or not, that are decided by the another input of the AND gate. Another input of the AND gate, which is nothing but the B. So if at all the B input is a 1, if at all the B input is a 1, then only whatever the pulses we are applying, those are fed as an input to the counter. If the B input is 0, then the output of the output of the AND gate is a 0, because as we know that if one of the input of the AND gate is a 1, then the output of the AND gate is nothing but the another input. Okay, if the one of the input of the 0, if the one of the input of the AND gate is 0, then the output is 0. Okay, if the one of the input of the AND gate is a 1, then the output of the AND gate is nothing but the other input, which is nothing but the A, and these pulses are fed as an input to the counter. These pulses are fed as an input to the counter. Okay, so just remember that one. Okay, so now coming to the rest of the blocks. So as I told you that this is a switch now. So to this is acting as a switch, and to this particular switch we should apply the 1 as well as a 0. Means whenever we are applying whenever we are making this input as a 1, this B input as a 1, at that time the counter is counting the number of pulses. Whenever we are making this input as a 0, the B input as a 0, then the counter is stopping the counting the number of pulses, counting the input pulses. Okay, so how to make this B input as a 1? That is decided by the flip-flop 1 and the flip-flop 2. That is decided by the flip-flop 1 and the flip-flop 2. So based on these two flip-flops, this gate takes the responsibility to generate the start signal, which is nothing but the 1. Okay, this gate takes the responsibility to stop the gate. This AND gate takes a responsibility to start the gate, which is called as a main gate. To start the main gate, this gate takes this AND gate takes the responsibility to stop the main gate. This AND gate takes the responsibility to stop the main gate. That's open the main gate. Okay. So now let us see. In order to realize this concept, I'm having the two flip-flops now. Initially, I'm assuming that the input means this particular flip-flop output is 1. This particular flip-flop is output is 1. Or I can say that the flip-flop 1 is set. Set is nothing but the 1. Reset is nothing but the 0. So when the flip-flop output is set, when flip-flop output is set means we have the output, if you want to remember the what is that the block diagram of that the flip-flop, the block diagram of the RS flip-flop. Okay, so I'm assuming that this is the SS signal and this is the R signal, and obviously we have the two outputs. One is the Q and Q naught. This is a Q and it is a Q bar, active low and active high output. Okay, so just like this we have the Y and the Y bar. When we can say that it is a this flip flop is set, obviously Q is a 1, Q bar is a 0, because it is a inverted. Q bar is a 0. So we have the 1 over here and 0 over here. Okay, so let us let us go with the 1. Okay, so if this one is a 1, this one is a 1, so this one is applied as an input to the one of the AND gate. Okay, so this one is a 1, obviously A is a 1. So when the A is a 1, as I told you that if one of the input is a 1, then the output of the AND gate is nothing but the another input. So another input of the AND gate is nothing but these are the time-based selector. It is a time-based selector, means it is generating the pulse signals. It is generating the pulse signal. So whatever the time-based selector we have seen, that is a this block. Okay, this block is indicating that particular time-based selector, and these pulses are given as an input to this particular AND gate. Okay, so means I'm assuming that this one is a 1. Okay, so this one is a 1, this one is a 1. So when these two inputs are 1, then the output is a 1. When this one output is a 1, then obviously what will happen? This signal is a this output is of the AND gate is a 1. Then obviously this is a 1. So if the flip-flop 2 set signal is a 1, so set signal is a 1 means S input is a 1 means output is equals to the 1. So output equals to 1 means Y output pin is a 1. Y naught pin is what? Y naught pin becomes a 0. So when the Y naught pin becomes a 0, obviously what will happen? The input of the AND gate, one of the input is the pulses, another input is a controlling signal. So if the another input of the AND gate is a 0, then obviously the counter is not counting the pulses. Means the pulses are not feeded as an input to the counter. Pulses are not feeded as an input to the counter. So means which is stopping the counting. So now this gate is acting as a stop. This gate is acting as a stopping the counting. This gate is acting as a stopping the counting. Okay. Now let us go in the reverse order. So other way of thing is initially we assume that the flip flop one output is a set. Now in order to start the counting, what I'll do is I'll apply the R input as a 1. I'll apply the R input as a 1 to the first flip flop. We call that one as a read pulse. When the R input is a 1, then obviously it is acting as a the flip flop is in the reset mode. So flip flop is in the reset mode means output of the flip flop is a 0 and this output signal is a 1. So if this output is a 0, then obviously this gate, one of the input of this gate is a 0 na, then the output is equals to the 0. And if you come to this output is given as an input to this particular AND gate. And one input of the AND gate is a 1, then obviously output of the AND gate is nothing but the other input. Other input is nothing but the B, which is connected as an input to the connected to the time based selector. So this time based selector is generating what ma? Pulses. This time based selector is generating the pulse. Okay, it is generating the pulse. So because of that, the output of this gate is a 1. So the output of this gate is a 1, which is applied as an input to this particular flip flop 2. So when it is applied as an input to the flip flop 2, which is a R input, then obviously output is a 0. So output is a 0. This output is 0 because previous output of the what I mean to say that the output of this gate is a 0 na. The same output is connected as an input to this particular flip flop 2. So this one is a 1 and this one is a 0. Obviously the flip flop 2 will enter into the reset mode. When it is entered into the reset mode, output of the flip flop is a 0. Output of the flip flop is this Y output is a 0. Another Y bar output, which is a Q bar output, is a 1. So when it is a 1, then the pulses when it is a 1, the one of the input of the AND gate is a 1, then the output of the AND gate is nothing but the output of this AND gate is nothing but the another input, which is nothing but the pulses. So these pulses are fed as an input to the counter. These pulses are fed as an input to the counters, and the counter is the one which is counting the number of pulses. Okay, so number of pulses. Now what we are expecting that the pulse the time based selector is selecting the time, means for a particular time period this switch is closed. Because of that the pulses are fed and this switch is open now. So how this switch will becomes open means we have the pulse now. So this particular duration, the pulse duration, we have the 1 over here now. This particular one is given as an input to the flip flop 2 as well as the input to the flip flop 1. When this particular one is a 1, it will complement. 1 means it will toggle. So toggle means previous one is a 0, now it becomes a 1. So as it is becoming the 1, at that time what will happen? This is a 1 and this one is generating the output of this as one of the input of this one is a 1, then the pulses are fed as an input. Now the output of the AND gate becomes a 1. So when the output of the AND gate becomes a 1, that is a stop AND gate becomes a 1, then this one is a set now. So this one is a set means previously it is a 0, now it is a 1. So it is a 0 means again the switch will be closed. Means within the given time period only the switch is closed. Again the switch is open. I'm sorry. Again the when this becomes a 0, again the switch is open. So when the switch is open, then we don't have the pulses. Okay. So means this switch is closed only for selected time period. Within that time period, how many number of pulses are counted by the counter? How many number of pulses are counted by the counter, and these pulses are given as an input to the mathematical calculator, so which will take the ratio between the number of pulses. I'm assuming it as a n within the time period t, then it is nothing but which is equals to the frequency of the input signal, okay. So this is the explanation of your digital frequency meter. So remember that digital frequency meter main intention is to calculate the input signal frequency, to calculate the input signal frequency, we are taking the digital frequency meter. We are taking the digital frequency meter. So in this one, this is a showing the individual blocks of the digital frequency meter, and here we have the time based selector, and here we are having the block diagram. Here we are having the block diagram. One gate is acting as a start gate, another gate is acting as a stop gate, and based on the start gate inputs, the main gate will open and close. Main gate will open and close. Okay. So this is all about your what is it digital frequency meter. And here, if you want to include all the parameters in one diagram, the diagram looks like this. The diagram looks like this. So in this diagram, we are having the what is that input signal, and it is amplified by the amplifier, and the switch trigger is the one which is converting the sinusoidal wave into the square wave, and these square pulses are given as an input to the main gate, and this main gate is controlled by what ma? It is a switch. This main gate is acting as a switch na? So it is controlled by the what is that control signal. That control signal is nothing but the time based selector. Okay, so with the help of the time based selector, we are selecting the time period. Based on that time period, the switch is closed up to that time period, and again it will open the switch after that time period. Okay, after that time period, we have the counter which will count the signal, and finally it will perform the mathematical calculation by taking the ratio between the number of pulses counted by the counter by time period. So finally it will display the information on the screen. Finally it will display the information on the screen. Okay, so this is all about your digital frequency meter. So if you are getting if you are if you feel that more number of diagrams are there in the digital frequency meter, you can skip off this one. If you want, you can skip off this one. You can go with these three diagrams, but if you want a more simple way for the explanation, then better to use the first diagram. This is the basic diagram, and after that we can go with this one. You can go with this particular one, but you are supposed to give the clear explanation. You are supposed to give the clear explanation. We are not having the complete explanation about this particular block. So that's why you are supposed to draw these three diagrams especially. So if you are not having the time, you can skip up this one, but these three diagrams and the theory part plays a major role in the exam. Okay, so this is all about your digital frequency meter. The next one is a digital voltmeter. The next one is a digital voltmeter. Let me take, let's see the time. Digital voltmeter. Yeah, the main intention of the digital voltmeter is to measure the voltage of the input signal. To measure the voltage of the input signal, we are taking the digital voltmeter. To measure the voltage of the input signal, we are taking the digital voltmeter. There are two ways to measure the input, that is the voltage of the input signal. There are two ways to measure the voltage of the input signal. One is directly take the digital what is that input signal and apply that one, and it will measure the voltage and displays the information on the screen. Okay, now displays the information on the screen. But uh, how exactly this particular digital voltmeter is measuring the voltage of the input signal? So for that, what we do is we'll take the two inputs to one block. Means this digital voltmeter is taking the two inputs. Okay, one input is a known signal. One input is a known signal. Means we know the voltage of the this signal. I'm assuming that it is a input 1. Okay, I'm assuming that this is the input 1. So to the input 1 of the digital voltmeter, I'm taking the known signal. To the input 2, I'm applying the unknown signal. So this is a known signal, and this is a unknown signal. Okay, unknown signal. Okay, now, so when we take the known signal means we know the voltage of this particular signal. We know the voltage of this particular signal, and we don't know the voltage of this particular signal. So in order to calculate the voltage of this unknown signal, I'll always compare the known signal voltage with the input signal voltage. Known signal voltage with the input signal. Wherever these two signals are having equal amplitude, wherever we see that these two signals are having the equal amplitude, then I will lock the device and it shows that how much voltage is there at that point, at what point these two amplitudes are equal, these two signals amplitude are equal. At that point, how much voltage is there in the known signal, that is a voltage of the unknown signal. How much voltage is there in the known signal, that is the voltage of the unknown signal. Okay, voltage of the unknown signal. Remember, in order to calculate the voltage of the unknown signal, what I am doing is I am taking the known signal and I am taking the unknown signal. I am comparing the known signal with the unknown signal. I am comparing the unknown signal with the unknown signal. So using the comparator, wherever the output of the comparator is 0, wherever the output of the comparator is 0, then obviously the known signal as well as the unknown signal both are having the equal amplitude. So at that point, how much voltage is there in the known signal, that is the voltage of our unknown signal. That is the voltage of our unknown signal. Okay, now are we clear? So this is the basic idea about how exactly the digital voltmeter is able to measure the voltage of the unknown signal. How exactly the digital voltmeter is able to measure the voltage of the unknown signal. Let us take the diagram. Okay, now. So here, don't get confused. This is not the one diagram. It is a two diagrams actually. I'll show the border. Okay. So this is the diagram for operation, and this is the waveform explanation of your digital voltmeter. Yeah. Before that, let me take one more thing. So we have the digital voltmeter. Where are the parts? Right. So we have the different types of digital voltmeters now, depending on the input signal, depending on the I took the block now. I took the block like this. Okay, so I took the block like this, and I took the two inputs. One is the known signal and another one is the unknown signal now. Depending on the method which is followed by the digital voltage meter, means what kind of input signal they are taking, that is a known signal they are taking. Depending on that, the digital, there are different types of digital voltmeters. There are different types of digital voltmeters. Okay, wait a minute, it is wait a minute. I know the list, but let me show this. Okay, so we have the ramp type digital voltmeter. We have the ramped up digital voltmeter, integrating type digital voltmeter, potentiometric digital voltmeter, and successive approximation type digital voltmeter, continuous balance type digital voltmeter. Okay, so there are different types of digital voltmeters which are available in the market, but we are studying about the ramped up digital voltmeter. We are studying about the ramped up digital voltmeter. If you want, you can go with the integrating type digital voltmeter also, integrating type digital voltmeter, but if the time permits, I'll then last minute I'll explain the integrating type digital voltmeter, but I'll go with the RAM type digital voltmeter in this class. Okay, now don't get confused with this one, because no one will ask the specifically explain the RAM type digital voltmeter, the integrating type digital voltmeter. They simply ask the explain the digital voltmeter. So I'm just taking the RAM type digital voltmeter. So whatever the diagram which you are seeing on this screen, this is following the RAM type digital voltmeter. It is following the RAM type digital voltmeter. RAM type digital voltmeter. So here, let us go for the block diagram first. Let us go for the block diagram. This is a block diagram. Huh? So this part is a block diagram, and this is a waveform response. Wait a minute. Why I come across this one? Yeah. Oops. Wait a minute. Okay. So this is a block diagram and this is a signal response. I'll explain that one. So in the block diagram, I'm having the input voltage. I'm having the input voltage. Okay. So this input voltage is compared with the known signal. So here I'm taking the ramp signal generator. Na? So ramp signal generator is nothing but this signal I'm assuming it as a known signal. This signal I'm assuming it as a known signal, and it is the unknown signal. Means I know the signal voltage over here. I don't know the voltage of the input signal. Okay. So these two signals are compared by the comparator. These two signals are compared by the comparator. Okay. If at all the output of this comparator is a 0, the output of the comparator is a 0, then stop the means open this particular switch. We are having the starting and stopping gate, or I can say that it is a switch. Simple case, I can say that it is a switch gate, and this gate is closed or open. That purely depends on your what is that comparator the signal coming from here, the signal coming from here. If the difference between it is a comparator, na? If the difference between these two signal is some positive, then it will start the gate. Means it will close the gate. If the difference between these two equals to the zero, if the difference between these two equals to zero, then it will stop the operation. Or I can say that this output takes the responsibility to start the gate, and this output takes the responsibility to stop the gate. So now the thing is, how many number of pulses are supplied during the closing of the start gate? Those pulses are counted by the counter and finally shown in the output, and that is nothing but your what is that voltage of the signal. If you are getting confused with this one, let us go with what is that sine waveform in the waveform explanation. So here what I am doing is we are interested to calculate the voltage of the unknown signal. We are interested to calculate the voltage of the unknown signal. Is it or not? We are interested to calculate the voltage of the unknown signal. And this particular unknown signal voltage is compared with the known signal. I'm assuming that this is a known signal. I'm assuming that this is a known signal and whose voltage is 12 volts. Whose voltage is 12 volts. I'm taking the I'm generating the ramp signal, means it is linearly decreasing order. The signal is linearly decreasing. The linearly decreasing. As I told you that one is a known signal, another one is a unknown signal. These two signal amplitudes are continuously compared. So here I'm having the ramp signal, which is a known signal. It is reducing the value from the 12 volts to the minus 12 volts. It is a ramp signal. It is reducing linearly from the 12 volts to the minus 12 volts. So wherever this amplitude is equals to the known unknown signal amplitude, wherever this amplitude, the known signal amplitude is equals to the unknown signal amplitude, from there to means it will tick this particular point. Okay, it will tick this particular point, and the ramp signal is keep on reducing, and it is crossing, it is moving from the plus 12 to the minus 12 volts. Now whenever the ramp signal is crossed the zero level, whenever the ramp signal is crossed the zero level, it will mark this point also. So one marking point is it will mark the when the two signal amplitudes are equal. At that point we have one mark. When the ramp signal is crossing the zero level, we have the another mark. So between this gap, so or I can say that within this delay, I'll feed the pulses, I'll feed the pulses to the counter mark. I'll feed the pulses to the counter. So how many number of pulses which are counted by the counter within this period from the matching point to the zero level crossing of the ramp signal. So within this time period, how many pulses are counted by the counter? That is what your voltage of the unknown signal. That is what the voltage of your unknown signal. That is what the voltage of your unknown signal. Oh, clear? Okay. So means we are taking the known signal and we are taking the unknown signal, and both signals are compared always with the help of the comparator. So wherever we have the lock, we used to call this one as a lock, or I can say that it is a amplitude coincidence. Amplitude coincidence means both signals are having the same amplitude. From there means I'll take this one as a one locking point. I can say that it is a starting of the gate. It is a starting of the gate. At what point these two signals are having the equal magnitude, the from that point it is in the means that point is called as the starting of the gate, and it will close the gate, means this switch is in the starting mode only until the ramp signal cross the zero level. Until the ramp signal cross the zero level. Once the ramp signal cross the zero level, then it will take the this zero crossing as a another point, another locking point. Okay, so at the zero level crossing, this gate is a stop gate. This one is a stop gate. When this gate is open, at this point the gate is started. At this point the gate is open. Between this time period, how many number of pulses which are counted by the counter, that is what your voltage of the unknown signal. That is what the voltage of the unknown signal. That is what the voltage of the unknown signal. Are we clear? So that is what the voltage of the unknown signal. So now let us come to the block diagram explanation. So this is the signal explanation. We can easily understand. So block diagram explanation, I am simply applying the input signal, the unknown signal means I am applying the input signal whose voltage we are supposed to measure. So this signal is always compared with the comparator with the ramp signal. This signal is always compared with the comparator with the means this signal is always compared with the known voltage, which is nothing but the ramp signal generator. I am assuming that it is a ramp signal generator. So this particular ramp signal generator is generating the ramp signal, and it is always compared with this one. So this comparator is just, what is it? This comparator is comparing these two signals and giving the response. Whenever these two signals are having the equal magnitude, so it will, when these two signals are having the equal magnitude, it will generate one pulse to this particular gate to start the gate. Okay, so it will generate one pulse. So this pulse take the responsibility to close the switch. So when this switch is closed, then the clock pulses which are having over here, these clock pulses are feeded as an input to the counter, feeded as an input to the counter. Okay, so here this ramp signal generator is means at this point we have the equal, means when these two are equal, then the gate is closed, right? So this ramp signal is keep on reducing its amplitude linearly. So this ramp signal is again compared with the another comparator over here with the zero voltage, because we are supposed to consider on the zero crossing also. Whenever the ramp signal is crossing the zero voltage, at that time the output of this comparator is generating one more pulse to stop the gate, means the gate is open. To stop the gate means the gate is open, means the pulses won't be fed as an input to the counter. So within this period, within the start and stop period, how many number of pulses which are fed as an input to the counter, that is what your voltage of the input signal, that is what the voltage of the input signal. Okay, so this is the explanation of the digital voltmeter. So the digital voltmeter, there are different types of digital voltmeters available in the market. One is the RAM type digital voltmeter, integrating type digital voltmeter, potentiometric digital voltmeters, mixed trigger digital voltmeter, and so on. But in this class, we are discussing about the RAM type RAM type digital voltmeter. So in the RAM type digital voltmeter, I am generating the known signal. I am generating the RAM signal as a known signal, and I am comparing the RAM signal amplitude with the unknown signal. So whenever the both amplitudes are equal, that is taken as a starting point. Whenever the RAM signal is crossing the zero voltage, zero level, that is called as a stopping point. Within this time period, how many number of pulses are counted by the counter, that is what your unknown signal voltage, that is what your unknown signal voltage. Okay, so this is all about your digital voltmeter. So we studied about the digital frequency meter and the digital voltmeter. So we'll conclude this class. We'll continue in the next class with another kind of meter. Okay.